Over the years, many natural cryptographic constructions were found to be insecure. In response, modern cryptography was developed as a rigorous science where constructions are always accompanied by a proof of security. The language used to describe security relies on discrete probability. In this segment and the next, I'll give a quick overview of discrete probability, and I point to this Wikibooks article over here for a longer introduction. Discrete probability is always defined over a universe, which I'll denote by U, and this universe in our case is always going to be a finite set. In fact, very commonly, our universe is going to be simply the set of all n-bit strings, which here is denoted by 0, 1 to the n. So for example, the set 0, 1 squared is the set of all 2-bit strings, which happens to be the string 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 elements in this set, and more generally, in the set 0, 1 to the n, there are 2 to the n elements. Now, a probability distribution over this universe U is simply a function which I'll denote by P, and this function, what it does is it assigns to every element in the universe a number between 0 and 1. And this number is what I'll call the weight or the probability of that particular element in the universe. Now there's only one requirement on this function P, and that is that the sum of all the weights sum up to 1. That is, if I sum the probability of all elements x in the universe, what I end up with is the number 1. So let's look at a very simple example, looking back to our 2-bit universe, so 0, 0, 0, 1, 1, 0, and 1, 1, and you can consider the following probability distribution, which, for example, assigns to the element 0, 0 the probability 1/2, the element 0, 1, we assign the probability 1/8, to 1, 0, we assign the probability 1/4, and to 1, 1, we assign the probability 1/8. Okay, and you can see that if we sum up these numbers, in fact, we get 1, which means that this probability P is, in fact, the probability distribution. Now, what these numbers mean is if I sample from this probability distribution, I'll get the string 0, 0 with probability 1/2, I'll get the string 0, 1 with probability 1/8, and so on and so forth. So now that we understand what a probability distribution is, let's look at 2 classic examples of probability distributions. The first one is what's called the uniform distribution. The uniform distribution assigns to every element in the universe exactly the same weight. I'm going to use U between 2 bars to denote the size of the universe U, that is the number of elements in the universe. And since we want the sum of all the weights to sum up to 1, and we want all these weights to be equal, what this means is that for every element x in the universe, we assign a probability of 1 over U. So in particular, if we look at our example, the uniform distribution on the set of 2-bit strings would simply assign 1/4, the weight 1/4 to each one of these strings. And clearly, the sum of all the weights sums up to 1. What this means is that if I sample at random from this distribution, I'll get a uniform sample across all 2-bit strings. So all of these 4-bit strings are equally likely to be sampled by this distribution. Another distribution that's very common is what's called the point distribution at the point x0. And what this point distribution does is basically it puts all the weights on a single point, namely x0. So here we assign to the point x0 all the weight, 1, and then to all other points in the universe, we assign the weight 0. And by the way, I want to point out that this inverted A here should be read as for all. So all this says is that for all x that are not equal to x0, the probability of that x is equal to 0. So again, going back to our example, a point distribution, for example, that would put all its mass on the string 1, 0 would assign the probability 1 to the string 1, 0 and 0 to all other strings. So now if I sample from this distribution, pretty much I'm always guaranteed to always sample the string 1, 0 and never sample any of the other strings. So now we know what a distribution is, and I just want to make one last point, and that is that because this universe U is always going to be a finite set for us, we can actually write down the weights that the distribution assigns to every element in U and represent the entire distribution as a vector. So here, for example, if we look at the universe of all 3-bit strings, we can literally write down the weight that the distribution assigns to the string 0, 0, 0, then the weight that the distribution assigns to the string 0, 0, 1. and so on and so forth. And you can see that we can write this as a vector. In this case, it'll be a vector of dimension 8. There are 8 strings of 3 bits. And as a result, basically, the entire distribution is captured by this vector of 8 real numbers in the interval 0 to 1. The next thing I want to do is define the concept of an event. So consider a subset A of our universe, and I'll define the probability of this subset to be simply the sum of the weights of all the elements in the set A. In other words, I'm summing over all x in A the weight of these elements x in the set A. Now, because the sum over the entire universe of all weights needs to be 1, this means that if we look at the probability of the entire universe, basically we get 1. And if we look at the probability of a subset of the universe, we're going to get some number in the interval 0 to 1. And we say that the probability of this set A is the sum, which is a number between 0 and 1. And I'll tell you that a subset A of the universe is called an event, and the probability of the set A is called the probability of that event. So let's look at a simple example. So suppose we look at the universe U, which consists of all 8-bit strings, right? So the size of this universe U is 256 because there are 256 8-bit strings. Essentially, we're looking at all byte values, all 256 possible byte values. Now, let's define the following event. Basically, the event is going to contain all bytes, so all 8-bit strings in our universe, such that the 2 least significant bits of the byte happens to be 1, 1. So for example, if we look at 0, 1, 0, 1, 1, 0, 1, 0, that's an element in the universe that's not in the set A. But if we change this 0 to a 1, then that's an element in the universe which is in our set A. And now let's look at the uniform distribution over the universe U. And let me ask you, what is the probability of the event A? So what is the probability that when we choose a random byte, the 2 least significant bits of that byte happens to be 1, 1? Well, the answer is 1/4. And the reason that's true is because it's not too difficult to convince yourself that of the 256 8-bit strings, exactly 64 of them, 1/4 of them, end in 1, 1. And the probability of each string, since we're looking at the uniform distribution, the probability of each string is exactly 1 over the size of the universe, namely 1 over 256. And the product of these 64 elements, each one has weight 1 over 256, is exactly 1/4, which is the probability of the event A that we were looking at. So a very simple bound on the probability of events is called the union bound. So imagine we have 2 events, A1 and A2. So these are both subsets of some universe U. And we want to know what is the probability that either A1 occurs or A2 occurs. In other words, what is the probability of the union of these 2 events? This little U here denotes the union of the 2 sets. So the union bound tells us that the probability that either A1 occurs or A2 occurs is basically less than the sum of the 2 probabilities. And that's actually quite easy to see. So simply look at this picture here. You can see that when we look at the sum of the 2 probabilities, we're basically summing the probability of all the elements in A1, all the elements in A2, and you realized we kind of double summed these elements in the intersection. They get summed twice here on the right-hand side. And as a result, the sum of the 2 probabilities is actually going to be larger than or equal to the actual probability of the union of A1 and A2. So that's the classic union bound. And in fact, I'll tell you that if the 2 events are disjoint, in other words, their intersection is empty, in that case, if we look at the sum, at the probability that either A1 happens or A2 happens, that's exactly equal to the sum of the 2 probabilities. Okay, so we'll use these facts here and there throughout the course. So just to be clear, the inequality holds always, but when the 2 events are disjoint, then in fact we get an equality over here. So let's look at a simple example. Suppose our event A1 is the set of all n-bit strings that happen to end in 1, 1. And suppose A2 is the set of all n-bit strings that happen to begin with 1, 1. Okay, so n, think of it as 8 or some large number. And I'm asking now, what is the probability that either A1 happens or A2 happens? In other words, if I sample uniformly from the universe U, what is the probability that Either the least significant bits are 1, 1, or the most significant bits are 1, 1. Well, as we said, that's basically the probability of the union of A1 and A2. We know that the probability of each one of these events is 1/4 by what we just did on the previous slide. And therefore, by the union bound, the probability of the OR is, a quarter, the probability of A1 plus the probability of A2, which is a quarter plus a quarter. And we just proved that the probability of seeing 1, 1 in the most significant bit or 1, 1 in the least significant bit is less than 1/2. So that's a simple example of how we might go about using the union bound to bound the probability that one of two events might happen. The next concept we need to define is what's called a random variable. Now, random variables are fairly intuitive objects, but unfortunately the formal definition of a random variable can be a little confusing. So what I'll do is give an example, and hopefully that'll be clear enough. So formally, a random variable, denoted say by x, is a function from the universe into some set v. And we say that this set v is where the random variable takes its values. So let's look at a particular example. So suppose we have a random variable x, and this random variable maps into the set 0, 1. So the values of this random variable are going to be either 0 or 1, so 1 bit basically. Now this random variable maps our universe, which is the set of all n-bit binary strings, 0, 1 to the n. And how does it do it? Well, given a particular sample in the universe, a particular n-bit string y, what the random variable will do is simply output the least significant bit of y. And that's it. That's the whole random variable. So now let me ask you, suppose we look at the uniform distribution on the set 0, 1 to the n. Let me ask you, what is the probability that this random variable outputs 0, and what is the probability that the random variable outputs 1? Well, you can see the answers are half and half, but let's just reason through why that's the case. So here we have a picture showing the universe and the possible output space. And so in this case, the variable can output either 0 or 1. Well, when does the variable output 0? The variable outputs 0 when the sample in the universe happens to have its least significant bits be set to 0. And the variable 1 outputs 1 when the sample in the universe happens to have its least significant bit set to 1. Well, if we choose strings uniformly at random, the probability that we choose a string that has its least significant bit set to 0 is exactly 1/2, which is why the random variable outputs 0 with probability exactly 1/2. Similarly, if we choose a random n-bit string, the probability that the least significant bit is equal to 1 is also 1/2, and so we say that the random variable outputs 1 also with exactly probability 1/2. Now, more generally, if we have a random variable taking values in a certain set v, then this random variable actually induces a distribution on the set v. And here I just wrote in symbols what this distribution means, but it's actually very easy to explain. Essentially what it says is that the variable outputs v basically with the same probability that if we sample a random element in the universe and then we apply the function x, we ask how likely is it that the output is actually equal to v. So formally we say that the probability that x outputs v is the same as the probability of the event that when we sample a random element in the universe, we fall into the pre-image of v under the function x. And again, if this wasn't clear, it's not that important. All you need to know is that a random variable takes values in a particular set v and it induces a distribution on that set v. Now, there's a particularly important random variable called a uniform random variable, and it's basically defined as you would expect. So let's say that U is some finite set, for example, the set of all n-bit binary strings, and we're going to denote a random variable R that's basically samples uniformly from the set U by this little funny arrow with a little R on top of it. And this again denotes that the random variable R is literally a uniform random variable sampled over the set U. So in symbols, what this means is that for all elements A in the universe, the probability that R is equal to A is simply 1 over U. And if you want to stick to the formal definition of a uniform variable, it's actually not that important, but I'll just say that formally the uniform random variable is just an identity function, namely Rx is equal to X for all X in the universe. So just to see that this is clear, let me ask you a simple puzzle. Suppose we have a uniform random variable over 2-bit strings, so over the sets 0, 0, 0, 1, 1, 0, and 1, 1. And now let's define a new random variable x to basically sum the first and second bits of R. That is, x simply is the sum of r1 and r2, the first and second bits of r, treating those bits as integers. So for example, if r happens to be 0, 0, then x will be 0 plus 0, which is 0. So let me ask you, what is the probability that x is equal to 2? So it's not difficult to see that the answer is exactly 1/4, because basically the only way that x is equal to 2 is if r happens to be 1, 1, but the probability that r is equal to 1, 1 is basically 1/4, because r is uniform over the set of all 2-bit strings. The last concept I want to define in this segment is what's called a randomized algorithm. So I'm sure you're all familiar with deterministic algorithms. These are algorithms that basically take a particular input data as input, and they always produce the same output, say y. So if we run the algorithm 100 times on the same input, we'll always get the same output. So you can think of a deterministic algorithm as a function that, given a particular input data m, will always produce exactly the same output, a of m. A randomized algorithm is a little different in that it, as before, it takes the input data m as input, but it also has an implicit argument called r, where this r is sampled anew every time the algorithm is run. And in particular, this r is sampled uniformly at random from the set of all n-bit strings for some arbitrary n. Now what happens is every time we run the algorithm on a particular input m, we're going to get a different output because a different r is generated every time. So the first time we run the algorithm, we get one output. The second time we run the algorithm, a new r is generated and we get a different output. The third time we run the algorithm, a new r is generated and we get a third output, and so on. So really the way to think about a randomized algorithm is it's actually defining a random variable, right? So given a particular input message m, it's defining a random variable which is defining a distribution over the set of all possible outputs of this algorithm given the input m. So the thing to remember is that the output of a randomized algorithm changes every time you run it, and in fact the algorithm defines a distribution and the set of all possible outputs. So let's look at a particular example. So suppose we have a randomized algorithm that takes as input a message m, and of course it also takes an implicit input, which is this random string that is used to randomize its operation. So now what the algorithm will do is simply will encrypt the message m using the random string as input. So this basically defines a random variable. This random variable takes values that are encryptions of the message m, and really what this random variable is, it's a distribution over the set of all possible encryptions of the message m under a uniform key. So the main point to remember is that even though the input to a randomized algorithm might always be the same, every time you run the randomized algorithm, you're going to get a different output. Okay, so that concludes this segment, and we'll see a bit more discrete probability in the next segment.